All right, hello and welcome to Unit 6. Unit 6 is more hypothesis tests. So let's get right into talking about the unit and how this unit's different than last unit. In Unit 5, what we did was we talked about a specific parameter from a single population. So what that meant was we were dealing with something like, is the mean greater than 5? Is the proportion greater than 0.7? We dealt with specific proportions from one population or means from one population and tried to determine whether they were less than, greater than, or not equal to a number. In this unit, we're going to make a subtle change where we are going to start comparing two parameters from two populations. So we're going to be looking at, is the first mean bigger than the second mean? Is the first proportion not equal to the second proportion? And we're going to measure things like that. So instead of dealing with one parameter from one population, we're going to be dealing with two parameters from two populations. And that's the big change in this unit. So this process list of what we're going to do is going to look awfully similar to what we had last unit, where we are still going to be finding our hypotheses, we're still going to be selecting an alpha, we're still going to be finding a test statistic, finding a p-value, comparing the p-value to alpha, and then stating a conclusion. One big note that I have here is to keep track of which population is which. This will depend on the lesson, how important this is, but it's easy to get confused because we have two populations. So, just as an example, if we had something like population 1 being boys and population 2 being girls, well, if you were trying to prove P1 was greater than P2, it really matters that this is the boys' population parameter, or proportion value, and this is the girls' proportion value. If you just rename these, population 2 and population 1, now this whole inequality would flip. So it's really important that you pay attention to which population is which we'll talk about when we start setting our hypotheses of just being clear, communicating with yourself and the grader as to which population you're going to call which. So let's jump right into a problem. Okay, the table below lists results from a single random sample of front seat occupants involved in car crashes. Use a 0.05, so we're still looking for those key numbers, so that's our alpha. Significance level to test the claim that the fatality rate of occupants. By the way, when I see this word rate, that's telling me that this is a proportion problem, which all the problems in today's lesson are going to be proportion problems. So this means this is a proportion problem. So we're not dealing with mu, we're dealing with p. Of occupants is lower for those in cars equipped with airbags. Okay, so we have two populations. We have population 1 is the airbag population, and then we have population 2 is the no airbag. So you see right from the beginning of the problem, I'm going to make it really clear which population's which, so I don't get confused later on. So what this data is telling us is that 41 out of the 11,541 people involved in crashes with that had an airbag passed away. So 41 fatalities out of 11,541 incidents. And then what this is telling us is 52 out of 9,853 occupants died without an airbag. So, step 1 is going to be the same steps we've always had as a first step, is setting the hypotheses. Okay, so for the null hypothesis, you're always going to have it's going to be really simple. If it's a proportion problem, the null hypothesis is always going to be this. There's no number involved. It's just going to be that the first proportion value equals the second proportion value. So this is actually easier than Unit 5 because we don't even have to look for a number. We automatically know that the null is going to be that the two proportions are equal. If this were a mean problem, we'd be saying mu1 equals mu2. then we're going to have an alternative hypothesis. Well, we've got to be really careful here. This is probably the simplest place to make a mistake out of any of these problems. So what they tell us is, in the original problem, they say that the fatality rate is lower for those with airbags. So we want the airbag population proportion to be lower than the non-airbag. So we have written here that P1, population 1, that is the airbag group. So we want the airbag group, P1, to be less than the non-airbag group, which is parameter or population 2, so proportion value of 2. So this is saying right now that the proportion value for the airbag group is lower than the proportion value for the non-airbag group. Which, this claim makes sense. It's saying that there's a lower probability of dying if you have an airbag versus no airbag. Okay? And those are our hypotheses. It's really important to set this correctly. So it's really important that we know which population's which, and we have the arrow facing the right direction. We're saying that the airbag group has a lower, so less than, fatality rate than the non-airbag group. Okay, now we're going to set alpha. We saw from the beginning of this problem, they said that the alpha was 0.05. So alpha equals 0.05. Now we're going to move on to our test statistic. So here's our new test statistic. It's kind of a big one. There's a lot to this one. Okay, so this test statistic, it's z equals p hat 1, which would be the statistic, the sample proportion for population 1, minus the sample proportion for population 2. Now, down here you're seeing these new symbols for us, p bar and q bar. What p bar and q bar are, we can find down here. It's called a pooled proportion. So it actually takes all the all of the successes from each of the populations, smushes them together on the top by adding them together, and then it takes all of the sample sizes from each of the two populations and it puts those on the bottom. So basically what it's saying is the top for this example will be all of the people that died in car crashes, and then regardless of airbag, and then the bottom will be all of the people that were involved in car crashes. So it's a pooled proportion. It's not separating the two populations. It's putting them all together into one proportion. And then Q always is just 1 minus P, so Q bar is equal to 1 minus P bar. So we're going to have to do some work to fill this thing out. So I'm going to go down here like halfway, and I'm going to write Z equals, and make it a big fraction. And then I'm going to give myself a little space up here to do some of the calculating. Okay, so let's figure this out. So I'm going to go and find my P1 hat, which for population 1, it was 41 out of 11,541. Which I can go to the calculator to find out. I want to be really accurate here, so I'm going to go a few decimal places. I'm going to go 0.00355. And then I'm going to find P2 hat, which will be the second sample proportion for the non-airbag group. So 52 divided by 9,853. Which my calculator tells me is 0.0052, or sorry, 53. I guess I could go 28 if I want to go the same number of decimal places as the last one. And now we're going to do that pooled proportion, which I don't need to go back and look at the top because I can actually look at P1 and P2 to put this together. Okay, so the pooled proportion is the two x's added together and the two n's added together. These are the x's, and these are the n's. So I'm going to put these together, and when you do this, you need a parentheses connecting the numerator and denominator. So we're going to have parentheses 41 plus 52 divided by that big number, 11,541, plus 9,853. And we're going to see what that gives us. So our pooled proportion is going to be, I'm just typing this into my calculator right now, and I get an answer of 0.00435. And then while I'm at it, now that I have p hat, I can get, or p bar, sorry, I can get q bar, which would be 1 minus 0.00435. Which is 0.99565. So you notice there's a little bit more legwork to get going on this formula than we had last unit. That's probably the hardest part of these problems, is there's a little bit more effort up front. Okay, now that I'm ready to go, I'm going to use this formula that I see over here again. Okay, and we're going to start plugging that in. So P1 hat would be 0.0035 minus P2 hat will be 0.00528. So that was the top. And now we're going to go to the bottom, and we're going to have a big square root. This is going to be a little crammed, so let's be careful here. We're going to have P bar Q bar, which is 0.00435 times 0.99565 divided by N1, which N1 is the bottom of P1 hat, so 11,541. And then plus, same top, 0.00435 times 0.99565. And then the other n on the bottom, which would be 9,853. And that's just a loaded problem here. So we're going to make sure we're really careful putting this in our calculator. Okay, z equals, I'm going to make sure there's parentheses around my numerator. And then divided by square root. Square root acts as parentheses, so I kind of have parentheses already built around. Then I'm going to have to put parentheses around this numerator. So I'm going to put parentheses around here, 0.00435 times 0.99565. Then I'm going to put I can just put division here, 11,541, and then have addition because it's order of operations. But if you're a little nervous about that, you might want to go back and put big parentheses around this fraction just to be careful. So maybe I'll do that just to be super careful. I'll just go and insert an extra set of parentheses there around that fraction, and then do divided by 11,541, and I'll close that parentheses. Then I'm going to put plus. Then I'm going to do the same thing over here and put big parentheses around this fraction. So big parentheses, and then 0.00435 times 0.99565, and then divided by 9,853. This might take you a few tries to get right. It's probably the toughest thing we've typed into our calculator all year. So keep trying that. Let me know if you're having a tough time with it, and I can help you out. But hopefully you ultimately get an answer of negative 1.92. It's a z-score, so I don't mind rounding to the 100th. So a lot of effort went into that one, but there's our z-score. And then I'm going to come down here, and the rest should be, a little bit easier. We're going to follow the same rules we did last unit, where if it's, let's see, did I put that on here? No, it's going to be the same exact rules that we did last unit, where if it's a less than, we'll shade to the left. So maybe I'll put that in here. If it's a less than, we're going to go to the left. If it's a greater than, we're going to go to the right. If it's a not equal to and positive, we're going to go to the right times 2. If it's a not equal to and a negative, we're going to go to the left times 2. So for this problem, our alternative hypothesis was a less than, so we're going to go to the left. So we're going to say normal CDF. I guess I could draw the picture for you if you want. Okay, negative 1.92, and we're going to shade to the left. So we're going to go to the left, so it's going to be normal CDF, negative infinity, which we write as negative 10, comma, the z-score, negative 1.92, comma, 0, comma, 1. Okay, so just remember, left bound, right bound, 0, 1. Same old rules we've been doing for the last 3 units now. Okay, normal CDF, negative 10, comma, negative 1.92, comma, 0, comma, 1. So I'm going to go and type that into my calculator. And I'm getting a p-value here of 0.027. The conclusion is going to happen the same way it did before, where we're going to reject if the p-value is less than alpha, and we're going to fail to reject if it's not. Well, our p-value here is 0.027. If you remember, our alpha was 0.05, and that is true. It is less than 0.05, so that's true. So we reject the null hypothesis. We will reject because the p-value was less than alpha. One issue a lot of kids have in this particular unit is they want this to be based on the alternative hypothesis, but it's not. It's always a less than. When we determine our reject or fail to reject, we always do less than here, okay, regardless of what the alternative was. And now our conclusion, we're going to do just like we did last unit, except for now it's 2 proportions as opposed to a 1 proportion versus a number. So we're going to say, since we proved it, we proved that the alternative was true, within our confidence with our significance level. So we've got to say that this is true. Remember, this was the rate of deaths with airbags, and this was the rate without airbags. So we just showed that the fatality rate is lower with airbags. Okay? There is sufficient evidence at the 0.05 significance level to show the fatality rate is lower with airbags versus not having airbags. So that is our first problem today, walking you through everything, and now we'll go a little bit faster with the second problem. The second problem is very similar, but it's about seatbelts instead of airbags. So we have this problem is talking about people not wearing seatbelts. This evidence is talking about people wearing seatbelts. Okay? We're going to use a 0.05 significance level to test the claim that fatality rate is higher for those not wearing seatbelts. Okay, so the green there is our non-seatbelt group. The blue is our seatbelt group or population. And then we're going to test to show that it's higher for the non-seatbelt group. Okay, so we're going to start with our hypotheses. Null hypothesis. This is a proportion problem because we're talking about rates. Rates are proportions. So we're going to automatically say P1 equals P2. I haven't even decided what P1 and P2 are yet, but I know that's my alternative or my null hypothesis is that they're equal. The alternative. I always like to just do, so it's going to be no matter what. It's going to be P1 versus P2. Now, I always like to just call the first population I have information for P1 and the second population P2. So the first population was the non-seatbelt group. So this is the non-seatbelt. And then this is the seatbelt group. The claim says the fatality rate is higher for not wearing seatbelts. So that's saying that P1 is higher than P2 or greater than P2. So that's going to be our alternative hypothesis. Significance level was given to us as 0.05. So alpha equals 0.05. And we are ready to start getting our test statistic. What I am going to do on this problem with the spacing that I have available to me is I'm going to kind of go off to the side and calculate all of those little things that I needed for the last problem. So I needed my P1 hat, which will be 31 divided by 2823. Which gives me 0.01 or 110. I'm going to go 4 decimal places and it rounded to that. And then I'm going to need my P2 hat, which is going to be let's get rid of that and change the color. Our P2 hat is going to be 16 divided by 7,765, which would be 0.0021. Okay, and then we're going to need our P bar, which remember P bar is going to be the two n's and two x's combined. So that's going to be 31 plus 16 divided by 2823 plus 7,765. And that's going to be 0.0044. And then Q bar just equals 1 minus that. Which gives us 0.9956. And now I'm ready to actually go and get my Z value. So my Z equals P1 hat minus P2 hat. So 0.0110 minus 0.0021. And that's all over the square root of P bar Q bar. So 0.0044 times 0.9956 divided by N1, which was 2823, plus the same thing, P bar Q bar, divided by N2, which is 7,765, And that is going to give us a z value of, I think I might be able to squeeze it all in there. Okay, so take your time, type this in to the best of your ability, check mine to make sure you're typing it in right. Divided by the square root. And reach out to me if you're having a tough time with this. This is very tough to type in. I'm just typing it in right now, plus right at the bottom. All right, I'm getting an answer. Oh, it's a big one. 6.12. It's a big Z, so we're definitely going to reject. Okay, tucking this little side information off to the side and just keep going here. Okay, my p-value, because this is a greater than, we're going to go to the right, so it's going to be normal CDF. We're going to start with the Z since we're going to the right. Okay, if you need a picture here, I'm going from 6.12 off to the right. So I'm going to start at the Z, 6.12, go to the infinity, which we call 10, 0 and 1, and then we're going to see what we get there for that p-value. So we go to our calculator, second vars, normal CDF, 6.12, comma 10, comma 0, comma 1. Oh, it's a really small number. It's 9 zeros and then a 4. So really, really small. We are certainly going to be rejecting this. Okay, so now that we're here, we're going to say p-val, is it less than or equal to alpha? Well, is 0.000 less than or equal to 0.05? Yeah, that's definitely true. So true. So we reject the null. And when we reject the null, we put it into words that the alternative is true. Okay, so there is sufficient evidence to show that the fatality rate is higher without a seatbelt. This is real data, by the way, so if you didn't know that it was important to have airbags and seatbelts, now you do. Okay, and that's the end of that problem and the end of this lesson, and hopefully you feel pretty good about it.